So we'll start with the general organization. Systemic circulation, venous return to the heart is going to go into the right atrium. From the right atrium into the right ventricle out into the pulmonary trunk, to the pulmonary arteries, to the veins, to the lungs. And then the pulmonary veins back to the left atrium, from the left atrium into the left ventricle, and then ejected from there into the systemic circulation through the aorta. And on most of these, it's difficult to see the vessels on the back of the heart, so oftentimes the vena cava are torn off or cut off right at the base of the right atrium. And oftentimes the pulmonary veins are cut off right at the back of the left atrium. So that makes it a little tough to see those on like the sheep hearts and the ox heart, for example. All this stuff was cut off. So you'll have to look at several different hearts to see everything. Now, the valves reflect that pattern that I just talked about. So between the atria and the ventricles are large valves, the atrioventricular valves, and you can see the cusps of those by looking into the atria, or if you look up into the ventricles, you can see the cusps from beneath. The left atrioventricular valve has two cusps, so it's called a bicuspid or mitral valve. The right atrioventricular valve has three cusps. You can see this on the back here. That's what these flaps are here. They're cut away from the ventricular wall. And that, because it's got three cusps, is a tricuspid valve. And those names are synonymous, so you could use one or either. The valves going out of the ventricles into the pulmonary trunk or the aorta are called semilunar valves, and they don't have all of the chordae tendineae with them that I'll get back to in a moment. But those are much smoother cusps at the base of the pulmonary trunk and at the base of the aorta. And so those are called the pulmonary semilunar valve from the right ventricle and the aortic semilunar valve from the left ventricle into the aorta. And on this one, I've cut away a big chunk of the left ventricle here, so you can look all the way up to where the aorta starts and you can see the aortic semilunar valve. Now, the other structures that you'll find associated with the atrioventricular valves, you'll notice all these tendons here. These are the chordae tendineae that attach to the inferior edges of the cusps of the AV valves. And they help to prevent the AV valves from being pushed back up into the atrium when the ventricle contracts. And at the ventricular wall, those chordae tendineae attach to little bumps of muscle that you can see on some of these little extensions of muscle from the ventricular wall, and those are called the papillary muscles. And those papillary muscles help to pull on the chordae tendineae. When the ventricle is contracting, those papillary muscles contract as well, and that helps to tighten the chordae tendineae, again, to help from prolapse. So AV valve prolapse is when the valves are pushed back into the atria. Usually that happens on the left side, because as you can see, the ventricular wall is much more massive on the left ventricle than it is on the right ventricle. And so usually when you hear somebody talk about the AV valve prolapse, it's mitral valve prolapse, which means the left atrioventricular valve. Now, the reason that the left ventricle is so much more muscular than the right ventricle is that the left ventricle has to pump blood out into the systemic circulation, the aorta, and the resistance, the blood pressure in the systemic arteries is greater than the blood pressure in the pulmonary arteries. And so you need more force to get blood moving out into the aorta and the body than you do to get it moving out into the pulmonary trunk and the lungs. And in fact, if the right ventricle were as strong as the left ventricle, you'd have water buildup, fluid buildup in the lungs because you'd have too much pressure in the pulmonary vessels. Now, some of the other internal structures that we see on the walls of the ventricular chambers, you'll see bands of muscle, look like folds with little grooves that separate them, and those bands of muscle are called trabeculae. And trabeculae are muscle bands that help to provide force across the diameter or at least the periphery of the ventricle without taking up as much space as you would have to do if you had just solid muscle going across. So they act as muscular beams to help compress the ventricular chamber. And typically in the right ventricle there are one or two large trabeculae that go across the diameter of the ventricle, and those are called moderator bands. So here you can see kind of a broken moderator band, and I left a little bit of the right ventricular wall here so you could kind of orient that. And in the human right ventricle, there was a moderator band in one of these. You can see, oh, here it is. You can see a moderator, no, that's a papillary muscle. You can see a moderator band in one of the human hearts also that runs across the right ventricle. And that's found in the right ventricle, again, because the ventricular mass is a little less than the left ventricle. So that just helps to add a little resistance to extension of the chamber. And you can see that I did have one in here on the sheep. I think it's torn away here. This little band that went across the right ventricle in the sheep heart. And let's see what else. Oh, in the atria, if we open up, actually let's look in this one because you can see them really well in this. In the atria, you'll see this characteristic, kind of like trabecular orientation of bands of muscle. And these make up most of the wall of the atria, and these are called pectinate muscles, which are comb-like or feather-like. And again, those are to provide muscular force to compress the chamber without taking up a lot of volume. And you'll notice that the atrial walls are much thinner than the ventricular walls because those atrial walls, they don't have to generate much pressure. They're just letting, most of the blood is just going to flow into the ventricles through the AV valves during diastole, during rest. Now there's another structure in the atria that I think we can see. In the back of the atrium here is a wall, part of the interatrial septum that's very thin. And that is the Fossa Ovalis, which is, during development, there's a passageway, a flap between the left and right atria called the foramen ovale. And after you're born and start breathing, then that flap starts to seal up against the interatrial septum. And that becomes the fossa ovalis. And so you can see this little kind of thin spot. And usually it's easiest for me if I'm pushing in from both atria at the same time through the septum to find out where that little depression is. Let's see, what other internal structures? I think those are all the internal structures you guys have. Now for the external structures, when we're looking at one of the keys to identifying these structures, like on an exam, is going to be identifying what you're looking at. What orientation is the heart as you're looking at it? And so when you look at the heart, it's important to remember, okay, it's got this triangular shape with the base superior and the apex inferior. And if you're looking at the ventral or anterior surface of the heart, one prominent feature is the pulmonary trunk. It's going to be coming out at an angle on that surface from the right side. So when I find the pulmonary trunk like this, I know that I'm looking at, first of all, the anterior surface or ventral surface of the heart, and I know this is the right ventricle and this is the left ventricle. And then going along with that, and it's hard to see with the human hearts because they're so picked off, but you'll see a diagonal sulcus that runs across the right side of the apex. So the apex of the heart is all left ventricle. The left ventricle goes all the way down to the tip of the heart, as you can see in these sections. And then the right side is kind of slapped on the side of that. And they're separated by this interventricular sulcus. And so this is called the periconal interventricular sulcus because it runs beside the cone or apex of the heart. And in humans now we call this the anterior interventricular sulcus. On the posterior or dorsal surface, one key to that is the presence of the vessels going into the atrium. So the veins going into the two atria. You'll have the vena cava, the cranial and caudal vena cava, or superior and inferior vena cava, and you'll have the pulmonary lung or pulmonary veins coming in on the left side. So if you see those, then you know you're looking at the posterior or dorsal surface of the heart. And there is a sulcus running between the ventricles there as well. And that sulcus is the subsinus interventricular sulcus or the posterior interventricular sulcus. And the reason it's called the subsinus interventricular sulcus is because it sits immediately underneath or inferior to the coronary sinus, which is where blood from the heart is collecting and going into the right atrium. And I'll get back to that in a minute. So the backside is called the subsinus surface or posterior surface. The other thing I want to point out when you're looking at the ventral or anterior view of the heart is that you'll see the pulmonary trunk coming out of the right ventricle, as I mentioned, and immediately behind it is the aorta coming out of the left ventricle. And so these have a characteristic twist so that the pulmonary trunk is more ventral or anterior, more superficial, and the aorta comes out from behind that. Now, in place, in situ, this pulmonary trunk would go back and divide into the pulmonary arteries, which go to the lungs. And then the aorta would loop over the pulmonary arteries as the arch of the aorta, and then go behind the root of the left lung and descend down the thoracic wall behind the left lung, or dorsal or posterior to the left lung. Okay, the other thing I wanted to talk about is the coronary circulation and relating to these sulci and surfaces that I mentioned. One other sulcus that's important to remember when you're thinking about the coronary circulation is the coronary sulcus. And the coronary sulcus is really tough to see, especially on those guys. It's really tough to see because it's broken up by vessels. On the anterior surface, it's broken up by the pulmonary trunk and the aorta. But it is the gap between the atria and the ventricles. So the coronary sulcus goes around the right side and around the left side and divides the atria from the ventricles. And it's most important when we're thinking about the coronary circulation, because the coronary arteries are going to run out through that sulcus. As you can see here in these human specimens, at the base of the aorta, you have a left coronary artery and a right coronary artery, and you can see the aperture for that right coronary artery in the wall of the aorta. And if you look in here, we can see the left one